Hello everyone, I'm Adam. In this problem, what we want to do is find the equation of the plane that's passing through our 3 points, given here with coordinates, say 1, 2, 3, and the point with coordinate 3, 2, 1, and lastly with coordinates -1, -2, and 2. Now, to start with a couple of things that we know. Well, if we want to find the equation of a plane, we know that if we have, say, at least a point, say with coordinates x1, y1, and z1 in the plane, and some normal vector n to the plane with components a, b, and c, then we can find the standard form of the equation as a times x minus x1 plus b times y minus y1 and plus c times z minus z1, and that's equal to 0. So it kind of gives us a place to get started. Now, what we're going to consider, a little diagram over here, is we have the plane with our 3 points in it, and without loss of generality, let's just suppose let 1, 2, 3 be our point P. Say 3, 2, 1 be our point Q. And say the last one, -1, -2, 2 be our point R. Okay. Now what we're going to do is consider, well, first let's back here. We have at least one point. Well, we have 3 to pick from of a point that's going to be in the plane, but we need a normal vector. Now, how can we find a normal vector to a plane? Well, if we have, say, these 3 points in the plane, and that's going to give us, namely, 2 vectors in the plane. We'll say the directed line segment, say, from P to Q, let's call that U, and from P to R, let's call that V. We can find, right, a vector normal to the plane by taking the cross product of U cross V. Okay? So that's what we're going to do. Start by taking the cross product of U cross V to get our normal vector n, and once we get n, that's going to give us our A, B, and C, and then we can pick whatever coordinates we want to plug in the rest of the formula. So let's take a look at that. All right, so find our vector U. All right. So the directed line segment from P to Q, we'll find the component form. So subtracting our coordinates, so from Q, we're going to take 3 minus 1, and 2 minus 2, and lastly 1 minus 3. So that's going to give us our vector U as 3 minus 1 is 2, 2 minus 2 is 0, 1 minus 3 is -2, and V is our, say, directed line segment from P to R. And that's going to be found by taking -1 minus 1, say -2 minus 2, and lastly 2 minus 3. Okay, so our vector V, so -1 minus 1, we have -2, -2 minus 2, -4, and 2 minus 3, say -1. All right, so we have our U and our V, and now we want to find our cross product. All right, so U cross V. Now, again, when we find this cross product, we're essentially going to be following the same steps as finding the determinant of a matrix that would look like this, where our first row would be our unit vectors I, say J, and K. And then the second row would be the components of U, which we have as, say, 2, 0, and -2. And third row, the components of V, -2, -4, and -1. Now, this isn't a true determinant, but we're going to follow the exact same steps that we would as far as if this was a regular 3 by 3 matrix where our top row was constants rather than these unit vectors. But to follow our steps, right, what are we going to do? So how do we take the determinant of a 3 by 3 matrix? Well, we kind of start at the first entry in the first column, first row, and sort of blank that row and column out. And so we're going to take I times, right, the determinant of the 2 by 2 matrix that would be left with all the entries after taking out that row and column. So let's see if we can put this over here. Right. So we're going to have the determinant. Now again, starting positive, like we normally would, determinant of 0, -2 in our first row, and -4, -1, and that's times the unit vector I, and then minus the determinant, taking out our unit vector j in the column and the row, we have the determinant with 2, -2, and -2, -1 times j, and then plus, all right, the determinant. Lastly, taking out the column and row with k, we'd have 2, 0, and -2, -4, take the determinant of that, times our unit vector k. Okay, so to find this, we're going to go through and find the determinants of each of our 2x2 matrices. So again, remember when we're taking the determinant of a 2x2 matrix, we're going to take the product along the first diagonal, say 0 times -1, and then subtract the product going along the other diagonal. So 0 times -1 is 0, minus -4 times -2, which is a +8. So this determinant would be actually a -8. So we'll find our values first and then plug everything all together. Determinant of our second one will give us a -6. And lastly, 2 times -4 is -8, minus -2 times 0 will leave us with a -8. So what we have as far as our cross product, putting this together, is -8 I, say minus a -6, so plus 6 j, and minus 8 k. Okay? And again, the importance of this thing is this is equal to, right, our normal vector n. So now we have our, right, A, B, and C, our components of that we can now complete and plug into our standard form of the equation for our plane. So let's go ahead and do that. So we're going to have A times x minus x1. Now all we have to do is pick any point that we want. We can just go ahead and say pick the first point with coordinates 1, 2, and 3. So our equation is going to look like A, let's see, maybe come over here, -8 times x minus x1, or 1, and then plus B6 times y minus y1, or 2, and then, all right, minus 8, or C, times z minus z1, or we have 3. And that's equal to 0. So as far as an equation of the plane, this is what we have. So we could stop here if we wanted to, but we can clean this up just a little bit. So what we're going to do is distribute each of our numbers out in front, right, and kind of regroup terms. See if we can simplify this. So multiplying through by -8 here, we'll have, say, -8x plus 8, and plus, multiplying through with 6, plus 6y minus 12, multiplying through with -8, so -8z, and plus 24, and that's equal to 0. And so clean this up a little bit more. We're going to have, say, -8x plus 6y minus 8z, right? And +8 plus -12 plus 24 gives us a plus 20, and that's equal to 0. Okay, so again, we could stop here, but we're going to take this just a little bit further. If we notice, we can kind of reduce some of these terms, right? So we have -8, +6, -8, and 20. So we're going to take this and, say, multiply through all the way by, say, a -1/2. And so what's that going to give us? So multiplying through with a -1/2, we'll have, say, positive 4x, say, minus 3y plus 4z minus 10 is equal to 0. And lastly, if we want to, we could write this so that we have all our variables on one side and the constant on the other. So this could be equal to, or equivalent to, say, 4x minus 3y plus 4z is equal to, say, positive 10. So kind of a nice simplified form of our equation of our plane. Okay, so there we have it. Now, one last thing you can do is go back and make sure that we've done all our work correctly. And how can we do that? Well, if this is the equation of a plane with each of these 3 points in it, each of these points should be a solution to our equation down here. So if we kind of just spot check this, so our first point, right, we have x value, say 1, y 2, right, z is 3. So multiplying through 4 times 1, we have 4, would be minus 6 plus 12 is in fact a positive 10. Check our next point, where we have x value 3, y value 2, and z value 1. So 4 times 3, which is 12, right, minus 6 plus 4, again gives us a positive 10. And lastly, with x value negative 1, negative 2, and z being positive 2, so 4 times negative 1, so negative 4, plus 6, plus 8, again gives us a positive 10. So all our points are inside that plane since they satisfy the equation. So thank you very much.